the linear features themselves show high concentration of active regulatory proteins that control synaptic strength by regulating the shape of the spine and trafficking of receptor proteins in the synapse. So you can think of these as weighting coefficients in the neural network. That's the basis of our brain. So we'll move on now to look at the next slide. Give me a second to open. Okay. Then this image here is also from Dr. Glancy's laboratory. And in this case, this is actually two frames removing the first and the last that show that this is the dendrite, also the other hippocampal neuron, grown in the same way as the previous one, but not transected. It's got an internal membrane dye called FM464, and this is the image result after 10 minutes exposure to the dye, which has been internalized into the cell. As you can see, this is also a maximum V-stack. You can see great clusters of endosomes within the internal membrane system of the cell. The morphology of individual endosomes can be distinguished clearly, but the large endosomes do not move over large distances within the dendrite. However, you can also see smaller dendrite and smaller transformed vesicles, and the more mobile but carry very small amounts of membrane and dye, so are extremely difficult to image. And this was imaged at 1 MHz with the Clara, and the signal to noise ratio is extremely high, much higher than Dr. Blancy has been able to achieve previously. So we're here, and we are very happy about the results from that. As you can see here, that was the end of the CST22. Here, let's just have a quick look at the Clara, comparison of Clara specifications. You can see, compared with competitors, two market leaders, the deepest cooling with fan off, which is available on the model, the lowest breeze noise available at 1 MHz, and very competitive, equal to the best performer at 10 and 20 MHz. Not the highest frame rate because one competitor is minus 28 MHz, but because of our ability to vary vertical shift speeds in the camera at higher biddings, we can achieve high frame rates than even a camera running at 28 MHz. Because of our low noise performance at 1 MHz, we can achieve maximum dynamic range of any camera on the market. We have a sensor enclosed in a vacuum environment, which gives us maximum longevity, 14 and 16-bit digitization, comprehensive digital and analog I/O, and the hardware timestamp, which is the only one available on the market. And the Clara product that you've seen there, that is the entire camera. There isn't any large controller box that you have to hunt around or find a shelf for that sits on the side of the microscope directly. Okay, well, there is another camera that you might consider in very low light conditions, and I'll just quickly give you an overview of that. At the top you can see the interline CCD will give you a very poor signal relative to the Clara, where you can use the gain to benefit. But in the lower one, where you've got time to get photons, they send me to get high speed, then an interline CCD camera will provide you with best resolution and signal to noise ratio. So you can take a choice there. Quickly here, we're looking at the spectral responsivity of the two cameras. As you'll notice that the Sony Interline or the Clara provides you with two options. One where you can have extended range sensitivity, just by clicking an interface on this drive, so shift in a slightly different way. On the EMCCD has very good range response, but in the GSP area, it's less sensitive, has higher pixels, and probably higher noise than the Clara camera. So again, you'll choose these depending on the situation. I'm not going to tell you more about the but let's just have a look at the spectral range. You can see compared to 75 watt signal lamp, it's giving you enormously much more power in the UV, and also in the green and the orange areas of the spectrum. So this lamp will find a wide range of applications, even as far as using it for Fluorine 2 for calcium imaging device cells. So let's go and look at the DSD, because that is the newest technology that we're introducing here, or we're discussing here, and we'll be introducing later in the year, commercially. So just to remind you of the architecture of the system, all that runs around IQ workstation, bringing a light source on the left with every light out feed to the DSD, which has internal excitation and machine filters. It's a very compact solution, and will fit onto the side door of any microscope. So these are again reminding the key points of the spinning disc. I'll just you won't forget that, I won't re-emphasize its benefits, but I'll go on to look at how the system performs and why it performs in the way it does. So moving on. This is a schematic of the instrument, an optical schematic, and I will explain how this rather clever optical design that Tony Wilson and Remus and Mark Neal came up with, and how that functions. So if we start with the McNay light source on the right-hand side, you can see that the beam is collimated and then falls onto a dichroic mirror. So note the green is the excitation part and red is the emission part. So the excitation light finds its way through the spinning disc in this instrument, and is focused through the microscope objective lens onto the specimen. We get excitation of the fluorophore here, and we trace the emission light back through the objective, through the same optical path. The emission light will hit the disc, and the confocal light, the fraction of the white field light, will find its way through the disc. And on the right-hand side mirror there, I show that is what we call white field plus confocal. So the disc puts a pattern into the light, and the pattern that is in focus finds its way back through the light, plus some white field or an alpha focus light finds its way back through there as well. Now at the disc, we use both sides of the disc. The other side of the disc has the disc pattern here is made in aluminium. It's high reflectivity and has a hard coating, and so the light that falls onto the aluminium is reflected down into the other side of the instrument. And if you look at this mirror here, I've labeled this white field minus confocal. So all of the confocal light gets through the disc, but the white field light minus the confocal finds its way to the left. So now we have a symmetrical optical system, and we take this white field minus confocal, and it's reflected onto this image combiner or beam combiner. We have the confocal finds itself its way onto the other side of this combiner, and the two halves, or the two images, find their way onto the CCD camera here, which is the Clara. So we have a camera which has on one side white field plus confocal, on the other side the white field minus confocal. I'm going to talk about how those two get combined in a moment, but if you imagine simply subtracting those two, then you'll see you can either end up with simply white field, or purely white field, or purely confocal images. And that really is the beauty of the instrument. But let's look at the differential spinning disc itself.